Our next presenter is Kristin Yvonne Rozier of
Rozier.
My apologies, from Iowa State University. She'll be giving us a talk on From Unmanned Aerial Systems to Robonaut2. Whoops, my screen changed right as I was reading your title. Onboard runtime reasoning in air and space. Kristin.
All right, thank you very much. I'm here to give a bit of a status update on our runtime reasoning tool, and then I will highlight a few of the really cool use cases that have come out just recently. There are papers in 2020 for unmanned aerial systems, Robonaut2, and some other cases, so that will give examples of what the tool is really good at providing. If you could go to the next slide, please. First, we start with the question of how is flight software, and hit next slide. How is that different from just software? What are the unique characteristics that we really need to consider whenever we're making flight software? Next slide. Firstly, it has to work. So we have a commitment to think more deeply and thoroughly throughout the software design and implementation lifecycle about what verification tools we're going to use and how we're going to integrate them, how they're going to fit. Next slide. We also need capabilities for independent checks. Maybe these matter for regular software, maybe not so much, but definitely if we have flight software, we need some way, some fail independent way to know if something went wrong with it, if something went wrong with the system. So maybe we have a complex software algorithm that includes lots of nuances of how we're computing something, how we're arriving at certain, say, autonomous operational decisions, but it's really useful to have an independent sanity check, for example, that just makes sure that everything we're doing makes sense. And maybe that could be running a different, simpler algorithm that would give us insights and also provide a secondary check, another opinion on the system, so that we know if something's going wrong as early as possible, so that we can be reactive in the way we need to be for flight software. And next slide. Also, it's really great if we have transparent ties between anything that we're actually running on a mission with the verification tasks that we did when we were designing the software for that mission. So we might come up with really great sets of requirements, say for a protocol that we're building. We might do all sorts of verification to show that our protocol has all of the properties that we require in our system. And then, of course, we go and implement that protocol. We would do a lot of verification. For example, we might test that if our protocol is supposed to always do B whenever A happens, that in all of the tests, B happens whenever A happens. But then we, in some ways, sometimes throw out those requirements and then just run the software when we are launching it on an aircraft or spacecraft. And it's better and desirable if we could maybe also take those requirements, the ones that we verified hold in every case that we could look at as we were designing and implementing and building the software, and then independently monitor that, all right, system's running right now, and I have an independent check that is a sanity check on the side that whenever A happens, B is also happening, whether or not maybe the environmental conditions are the same as what they were when I designed and tested the software. Next slide. So to do that, we have a tool that we call R2U2, which stands for the capabilities that it provides for flight software. Specifically, it is responsive. It runs in real time. It is realizable, so it is easy to create instantiations of requirements that you would want to check in R2U2 from formalisms that are commonly used in operational concepts, and it is unobtrusive. So it fits in tight spaces. It has multiple different implementations. It can run in FPGA hardware. It has a C version that has been successfully hooked up in several different occasions to NASA CFS, for example. It has a C++ version, and these versions can run with whatever sort of constraints are required by the flight system. So if we can't mess with power or timing or other constraints, we have to fit into a very small space, we have to only use these resources, R2U2 can be shaped into whatever shape we need, and we can provide guarantees that we don't mess with anything that we're not allowed to. So it's unobtrusive. Next slide. Here's an example of a system that has an operational concept. It's actually really fascinating. I won't go into the details of this system other than to tell you that it's an automated airspace concept high-level architecture candidate that was proposed a few years ago at NASA Ames Research Center. And this is a highlight from its operational concept where there is a timeline. And this is the sort of thing that is really easy to represent in R2U2. You see this kind of thing a lot in ConOps for real flight systems, where you have maybe some different system modes, you have things that are happening in the environment and in the system, you have events on your timeline, and you have certain reactions that you're expecting to happen. And this is the kind of thing that's very transparent to represent in R2U2, and then launch runtime monitors to check that all of these things are happening the way you laid out on this timeline while your system's running. Next slide, please. So to harken back to a talk that you heard a couple days ago by Jim Dabney, you might, for example, be building something like a NASA Lunar Gateway, like he was building, and you might, in your ConOps, have requirements in the form of assume guarantee contracts. And generically, I have an example of what one of those might look like at the bottom of the slide here, and a link to Jim's paper. So in an assumed guarantee contract, you have some assumption that something happened, or it might be no assumption if you want to make sure that this requirement just always holds no matter what's going on. And in this case, I have a generic example of there's a command to start something. So if your assumption happens, if that's enabled, then I have a logical implies here, you have some output or some behavior that you want to guarantee happens anytime that assumption is satisfied on that same execution path. So you want to have a monitor that accepts both paths where the assumption doesn't happen, because then you're good, right? Assumption didn't happen, everything's fine. Or you want it to also accept where the assumption happens and then the guarantee happens, because also then you're good. That's exactly the behavior you expected. And you want it to flag times when the assumption happens, but then the guarantee that is supposed to follow doesn't happen. So we can do that with a logical formula, and I gave a little bit of a complex example here to show you some of the things we can express. The little box means that it happens, something happens continuously for the times in the little brackets. So in this case, we're going to say if we get some command to start something, then we have an action that holds for the next 6 seconds, if our time, like maybe we're accepting inputs or our channel is open or whatever, for 6 seconds that happens. And then we get after that a end command that this is ended and everything's been closed out. And in this case, I show an example of also having a little box with a 0 to 2 interval on there. That's a common thing we do to check and make sure that we didn't maybe sample at the wrong time or get an outlier or get a rogue signal, that we're really sure that it's ended because its status stays there for a little bit of time. So we're like, all right, yep, it's ended, it's switched state. We're really confident that it's in the new state. So this is an example of an assumed guarantee contract. And if you go to the next slide, we can encode these using formulas internally to R2U2. And in this case, the formula that I showed you for the assumed guarantee contract was in a logic that we call mission time linear temporal logic. And of course, linear temporal logic means the logic of timelines, linear temporal timeline. And it's mission time because it has annotations that say what times during your mission you want these certain things to hold. So this logic doesn't take all of that much in terms of a learning curve. It's pretty easy to pick up, and we can also, in the future, we're looking to make some automated interfaces where we can pull these formulas from common ConOps specifications. But You saw an assumed guarantee contract on the previous slide in this logic. It has things like the little box I showed you, which means always something happens continuously between these 2 points in time. And here I show you an example of always between 2 and 6. So you can see if we have clock ticks or seconds or whatever our units are on the right, that between 2 and 6 our thing P that we care about holds. We can also say that our thing P eventually holds within times 0 and 7 from now, and I show an example of that. We also can say more complex things like thing P happens until thing Q happens, and then we can put bounds on that. And I show an example of our thing P happening, and then we have our thing Q happening. And we can also have more complex than that even, where we have things like a release or button push operator, where we say pushing button P, if we choose to do that, will release thing Q from having to be true. And I show example of that also is that thing Q is true in the little time interval that we have, and we can push our button P. So we can say a whole lot of things in a pretty compact logic. Next slide. And then from this, R2U2 on the inside, you don't have to do anything for it to do this, automatically generates what we call asynchronous or event-triggered observers. So whenever we get new inputs into our observers, we're able to evaluate whether or not our requirements hold. So we evaluate with every new input. This is Boolean. We're not giving you some probability that your requirement holds. This is an absolute measure. Like we're sure you got the command start and then your action happened and it concluded at the appropriate time, or we're not. And because we're giving you an absolute true false value, we can give that to you as early as possible. In other words, as early as there is enough information in the system to be able to tell you that, but we can't necessarily tell you that, for example, when your assumption is happening, that your whole requirement is true, because there's some time involved there, right? We're not psychic and we're not projecting into the future that, oh, your assumption holds, and so therefore we know your guarantee is going to happen after this. We have to wait until we see the guarantee, and then we're like, yep, that happened, or nope, this didn't happen the way you intend. So for every clock tick, we resolve our formula or our monitor, which we're calling phi on this slide, for either the present time, if we're, say, for example, if we're sure that the assumption didn't hold, great. We know our assumed guarantee contract is fine because our assumption didn't hold, so we're not waiting for a guarantee, so we're good. I can tell you right now. Or if maybe we have an assumed guarantee contract and our assumption holds and we're waiting to see the guarantee, then we have to wait until a little bit later. Next slide. So this is an overview of the high-level architecture of R2U2. So in this case, we would get in sensor or software values from, say, for example, the system bus. And we would also have to reason over some system resource constraints that are supplied by the system design. And given this information, R2U2 is represented by the dashed box here. Then we have Boolean testers to populate the atomic propositions in our MLTL requirement representing formulas. So those are things like, is our altitude above our threshold? Or did we get the command to start something? Then this goes into our MLTL formula, or in this case, the example I've been using as a running example, maybe an assumed guarantee contract. And then we get a stream of verification results. So we get not just from the beginning of your mission, did this contract hold one time, but we continuously check. So say if we're using a unit of system clock ticks, then at every execution path that starts at every clock tick, we give you an output as to whether your requirement, say your assumed guarantee contract, held starting from that time. So we would start at the beginning of the mission and say, okay, our assumption didn't hold, so great. True, we're good. Maybe our assumption doesn't hold again. Great, true, we're good. Maybe then our assumption holds. And so we wait and see if the guarantee holds and we say we're good. And then we're still monitoring, right? So the next clock tick, we say, okay, now our assumption doesn't hold again. We're still good. So we monitor throughout the whole mission. You don't have to reset anything. And we're able to provide continuous feedback to the system as to whether it, during runtime, during execution, is still satisfying all of those requirements that we spent so much time time and effort designing at system design time. Next slide. So here is a real example where, say, N at the top is our timestamps that maybe represent system clock ticks. And then the lines below, the 3 lines below, represent input from our system bus in terms of, say, for example, sensor signals. And if we look at the middle one of those 3 lines, we can say that R2U2 is getting in the information, maybe a float value for the pitch. And then it's running this value through a Boolean tester that checks if the pitch is greater than or equal to 5 degrees. And that internally to R2U2 gives the output you see in the middle line there. And then R2U2 is monitoring that it wants to know, for example, if we satisfy a requirement of our pitch being greater than or equal to 5 degrees for 5 continuous clock ticks of the system. So that's what that formula means in the middle. And the bottom shows the output of R2U2 that it can send to other parts of the system. So for example, for the clock tick at 0, it's going to say false, because you can see, if you look at the middle line across the top of the slide, that the pitch was already at timestamp 0, not greater than or equal to 5. So we know right now this requirement doesn't hold. And the same for time 1 and the same for time 2. At time 3, our little pitch line inside R2U2, where we're filtering the pitch that we're getting from the rest of the system, goes to true. So now we can say, oh, well, sort of it might be true. We can't actually answer because we, again, aren't looking into the future. This isn't predictive. So it means we need to wait 5 time steps and see, all right, did this hold? And actually at time 8, you can see at the bottom, we are now sure, because we've seen 5 time steps, that that formula, that requirement was true for the execution starting at tick 3. And similarly at time 9, we know it was true for the one starting at tick 4. And at time 10, we know it's true starting for the time execution from clock tick 5. Then at clock tick 11, we know, looking at that top formula for pitch, that we did not have our formula of pitch being continuously for 5 clock ticks true, above 5 degrees for 5 clock ticks, that was false for times 6 through 11. So then we kind of catch up. And you can see it goes through the rest of the sensor data that it's reading in a similar fashion. Next slide. So one really interesting case study that happened in the year 2020 that we just published this past fall was we were able to add R2U2 to a UTM system, a UAS traffic management system that we were looking at as a candidate for integrating UAS into the national airspace, or the NAS. We were able to look at running R2U2 both on individual aircraft and on a ground station. And we caught some really interesting things that actually happened. Like, for example, there was a software conversion bug at one point where we hooked up multiple UAS to the ground station, and somehow the flight plans had a little bit of data corruption where their end times for some of them actually happened before their start times, which is, of course, a sanity check that a human would pick up that the software is assuming doesn't happen, but is very important to flag before you start trying to analyze these flight plans and your software goes into a rabbit hole you didn't anticipate. So R2U2 was able to pick that up. And the paper at the bottom of the slide has a very extensive website with a whole bunch of examples of all of the specifications, running them over real data, and a lot of how-tos in order to set this up on your own UTM system or a similar one. Next slide. We also recently published a study where we embedded R2U2 in hardware this time in the FPGA that controls Robonaut2's knee. And so you can see me with Robonaut2 on the left-hand side of the slide. And on the right-hand side, you can see a photograph that we have doctored a little bit of the interior joint of his knee. And there was a position error that was happening that had that happens very infrequently. So it was unrealistic to expect this to come up, even with extensive verification ahead of time. But it's really nice to be able to embed a sanity check where whenever we get a joint position error, we're able to disambiguate the source of the error and then automatically trigger a mitigation so that Robonaut2 can figure out exactly in which way his joint is being pulled off and then fix it himself automatically. And this is all transparent to anyone else interacting with the robot. So examples of that are in the publication at the bottom of this slide. Next slide. So here is a summary of some of the uses for R2U2, and it's available free and open source from a download page linked at the bottom of this slide. So one thing that a lot of people used it for is data integrity. It's really great for monitoring independently, all sorts of assumptions that your data is consistent, that it's coherent, that it is in line with your expectations. So if you think your altitude is a certain height, that your altitude really does remain in the expected range, that sort of thing. It's also really great for sanity checking. So any common sense assumptions, like with the UTM system, that a flight plan obviously has to start before it ends and not the other way around. These happen alarmingly frequently, especially as we move to more and more automated systems. So it's really nice to independently have a sanity check that's with a very simple, transparent algorithm that fits in small spaces. So we can just know if something went wrong and check ourselves and not use maybe data that's been corrupted. It's also really great for fault mitigation. So if there is a particular fault signature that you want to monitor for, it's usually very easy to encode. Okay, I never want to see this, right? I never want to see this happen, and then later this happened, and with this also is happening simultaneously. If I see this, that means there's something wrong, and I immediately want to trigger my mitigation. R2U2 is really great at that sort of thing. We've also used it for security monitoring. So we have another paper where we looked at some very complex temporal patterns that indicated that our UAS might have been breached by a potential GPS spoofer or some other hacker. And so we have a sequence of potentially slightly off nominal events that aren't terrible, and we can detect those also in real time. And it's also really great for mission integration. So for example, there was recently a rocket where the people who had assembled it had hooked up some of the connectors slightly incorrectly, but they passed all of the initial checks. And R2U2 is great at doing things like catching misconfigured or faulty tenuous connections that can elude some of those initial system integration checks, especially if maybe something's connected just well enough and then its state changes and becomes more tenuous during the mission. And I'm happy to answer any questions.
All right, thanks a lot, Kristin. We do have a question in the Q&A from Alexandra Holloway of JPL. Have you tried to apply R2U2 to deep space network track support?
No, but I would love to try that. So if you have any ideas or if you want to collaborate, please email me. We did publish a paper at AIAA SciTech this January, so just a few weeks ago, where we looked at putting R2U2 on a CubeSat and monitoring for different communication system faults. And we did some preliminary work there, but I would love to explore other kinds of space missions.
All right, next question is from Matthew Benson, and can we get your email address? And you can, if you're comfortable doing that.
Yes, yeah, I can put it in the chat. Here it's kyrozier@iastate.edu. And so I'll also put that, it's in the chat now.
All right, excellent. Okay, any other questions for Kristin? Okay. Thank you very much, Kristin. Excellent talk. Thanks for your contribution to Flight Software Workshop.